All right, so we're looking at 3.4 rational equations. And what I'm going to do is I'm going to do this in two parts. So you'll see 3.4a, that's this video, and 3.4b, which will deal with some word problems, and that will follow this video. So today we're just going to work on the first example without the word problems. Okay, so a rational equation, we could think of that as an equation that involves fractions, and so we've dealt with those before in just working with fractions and solving equations. Although right now we're looking at fractions that contain variables, and so solving for the variable even if it's in the denominator. So we're going to deal with it the same way we may have in with fractions. So I'm just going to show an equation that contains fractions. And then we'll come back to the note package here in 1 second. So if we had an equation like this one, let's say we had x over 3 plus x minus 5 over 2 equals 5, something like that. Then we're looking at one thing you might have done when solving these equations was to multiply the entire equation by whatever it takes to get rid of the denominators. So for instance, the first fraction has a denominator of 3, and so we can multiply that fraction by 3 in order to get rid of the denominator, but we'd have to multiply every term by 3 then. However, multiplying the first term or the whole equation by 3 does not get rid of the second denominator. It only gets rid of the first one. So what we want to do is we actually want to multiply the entire equation by the lowest common denominator, which in this case, with denominators 3 and 2, the lowest common denominator is 6. So we're actually going to multiply by 6, the lowest common denominator, and we could even write that as 3 times 2. So multiplying the whole thing by 3 times 2. And by doing that, we would cancel the denominator in the first expression, we would cancel the denominator in the second expression, and on the other side of the equation, the 5 would just get multiplied by both factors, 3 and 2. So what we're left with is we're left with the 2 and the x in the first expression, the 3 times the x minus 5 in the second expression, and a 5 times the 3 times the 2 in the third expression. So we're left with an equation that doesn't contain any fractions. And so we can solve this equation easily, or more easily at least, because we don't have the fractions to worry about with their denominators. So we'll continue this here just for the sake of the question. And so x equals 9 in this case. Now, we're going to apply these same ideas to the rational equations, where we're trying to multiply the entire equation by a lowest common denominator. So, we can see some definitions here. An equation involving one rational expression, and then we have the steps right here. So we'll follow those as we go through example 1. So to solve the equation, the first thing we want to do, like it says in the steps, is to factor, and that's obviously common with whatever we've been doing in this unit. Is we have been factoring. That's a big starting point for us. So in the left side of the equation, everything is factored already. So we don't have any factoring to do there, but we do have factoring to do on the right side. So this y squared minus 9y plus 18, that would be factored out to be y minus 6 and y minus 3. So we can see that our common denominator now, the lowest common denominator, is y minus 6 and y minus 3. That's the lowest common denominator. And so what we need to do is multiply every term by that lowest common denominator. Now, when we do that, we'll just write this up like this. For each term, so it's a little bit congested here. So feel free to pause the video so you can see this, or to clarify things, send me a message. But we're multiplying every term, every expression on both sides of the equation by that lowest common denominator. Now you might say, well, why aren't we multiplying top and bottom? Isn't that what we have to do? Multiply top and bottom by that? But because this is an equation, we're not changing the ultimate value of anything, or the equation in general, if we multiply both sides by this, every term on both sides by this, because it's an equation. And so what we have in our first expression, we see that the y minus 3's would cancel, because we have a y minus 3 in the numerator now, and then a y minus 3 in the denominator. We have a y minus 6 in the second expression, so that's canceling as well. And then we have a y minus 6 and a y minus 3 in the third expression, so that all cancels. So we can see what we're left with. So let's see what's left then in the next step. Once we've canceled those pieces out, we can see that we have a 9, the 9 that was in the numerator before, along with a y minus 6, because the y minus 3 canceled with the denominator, so we don't have a denominator anymore either. In the next expression, we have a 4 that was there in the numerator, times the y minus 3. The y minus 6 canceled with the denominator, so we again don't have a denominator in that expression. In the last one, on the other side of the equation, the y minus 6 and the y minus 3 cancel, leaving us only with an 18. So now we have an identical equation, but without any denominators. We've multiplied everything by what was necessary to eliminate those denominators. And now we have an equation we can solve just by conventional methods. Don't have to worry about any denominators. Simplify both sides and isolate y. So we have 9y minus 54, and careful of your sign here, minus 4y plus 12 equals 18. So we can see we have 5y on the left side, combining terms. And then on the right side, once we subtract 12 and add 54 to the right, we have minus 12 plus 54. I think we have 60. And then when we divide both sides by 5, we have 12. Left with 12 here. Now, in terms of the solution set here, in the last chapter, we needed to check our answer, the solution that we may have obtained because of those things called extraneous roots. In this chapter with rational equations, we don't have to check because we're not using any techniques throughout the question that only work sometimes in one direction. So we don't have to do a check here. What we do have to watch for is our non-permissible values. So let's list our non-permissible values. It does ask us to do that in the question itself. So the non-permissible values, same thing with the rest of the chapter. We're looking at the factors that we have, and we're noticing here, even though we canceled all of them out, we're looking at these factors here. So we have a y minus 6 and a y minus 3 as our factors. So we know that y cannot equal 6 then, positive 6, y cannot equal 3. Those are the two non-permissible values. Those are the two different based on the two different factors that we have in the question. So we look at our solution here. y equals 12, and that's fine. It's not a non-permissible value. It is allowed in terms of the math, and so we're fine with that being a solution. No formal check is required. Now, obviously you could do a check, substitute it into the equation, you'll find out that it does work. So, moving on to the next example, 1b. There's our previous stuff. Here we are. 1b, a similar question, but we actually have a variable in the numerator now, so we'll see what that looks like. But the same story in terms of how we begin and how we go through it here. So we do want a factor to start out, and similar to the last question, both terms on the left side don't contain any expressions to factor. Everything's factored already. And on the right side, be careful with that negative sign there, but we do have that denominator that can be factored. That would be x minus 3 and x plus 2. And you notice that this works out very nicely. You know, you see the factors here, and they do line up with the ones on the left side in those expressions. And that tends to be the way that things work, not all the time, but again, these questions are set up in a way that streamline things like that to an extent. So, in the same way as our previous example, we want to multiply everything by a common denominator, and our lowest common denominator, again, is just the two factors that we see, x minus 3 and x plus 2. Okay, every denominator contains part of that, and so the rest of it would be included here. So in this case here, we have a denominator of x plus 2. It needs an x minus 3 as well in order for it to be that lowest common denominator. So when we multiply, we will multiply by the x minus 3 and the x plus 2 to this first expression. And it's an equation. We're going to do it to every term that we have in the equation. So x minus 3 and x plus 2 gets multiplied. So because we're multiplying, we're only multiplying that to the numerator, and we're doing that to each term in the equation. That means we have an x plus 2 in the top of the first expression and the bottom as well. So the x plus 2 then cancels, leaving us with, and we'll do this in the next step already, leaving us with the 3x in the numerator that was there already, times the x minus 3 that we multiplied. The x plus 2 canceled with the denominator, so it no longer is there. In the second expression, we'll see what happens here. We have an x minus 3 in the top and the bottom. So we've canceled that. And again, the idea is to cancel these denominators, so there should be some canceling that happens in each term. X minus 3 on the top, x minus 3 on the bottom. Leaving us with a 5 and an x plus 2. So the 5 that was there to begin with times the x plus 2 that we've multiplied by. And on the right side of the equation, everything is canceling, meaning all the denominators. So the x minus 3 is canceling top and bottom. X plus 2 is canceling top and bottom. So we're just left with the negative 25. So we have, again, no more denominators in our equation, meaning we can solve this just by simplifying and solving the equation, maybe by isolating the variable. So we'll see what this looks like here. So we multiply here, get rid of the brackets. Now we see we have a squared term here. And so because we have a squared term, we can't just isolate x. We know this based on previous equations with our quadratics and so on, is that since we have the squared term, we have to solve this as a quadratic equation, meaning we want to get everything on one side of the equation. So let's get everything to the left. We have 3x squared minus 14x, and then bringing that 25 over, we add 25 to both sides, so we'd be left with 15, positive 15 on the right. So now when we are looking to solve this here, again, I would say factoring is probably the quickest way to go, although because this is a complex trinomial, the a value is 3, you might want to, if factoring is not your strong suit, you might want to avoid that entirely and just go quadratic formula. So you're welcome to do that, but I think that it's important not to shy away from these things because we might actually need to factor things like this, and so for you to be able to do that is important, particularly when you're practicing. It would be one thing on a test maybe to make sure you're right, but for practicing in assignments and examples, it may be a good thing to work on factoring this here. So you can do that on your own if you want to pause it and just to see if you can factor this here. I'll just write down what the factors are. So the factors here is 3x minus 5 and x minus 3. So we can, if you wanted to check that, we could also FOIL that and see that it does get us back to the original trinomial here. So now that we have our two factors, we know how to solve this. 3x minus 5 could equal 0, or x minus 3 could equal 0. And so in the left one here, we solve for x. So x would be 5/3. And in the other factor here, we solve for x. X could equal 3. So we have 5/3 and 3 as solutions. Now again, we don't need to do a formal check with this, but we do want to consider our non-permissible values. So let's do that right now. Our non-permissible values, we're looking at the factors that occur throughout the question. So I'll just scroll up a little bit here. We're looking all the way back up here. Our non-permissible values, before we canceled and everything, what were our denominators? Well, we see that we have denominators throughout here, x plus 2, and we have x minus 3. So two different factors, just like before in the previous example. And so our non-permissible values would be 3, x can't equal 3, and x can't equal -2. So those are our non-permissible values based on the factors we have in the question. So now, as we're looking at our potential solutions that we outlined, x can equal 5/3 and x can equal 3. Those are our potential solutions. Well, we see that not both of them do not work, or there's one that doesn't. And because of our non-permissible value right here, x cannot equal 3, and so this solution, this is a non-permissible value. So if it's a non-permissible value, that means it cannot be our solution. X cannot equal 3. So our only solution is the 5/3 then. So I would like to see from you, if I was seeing this on a test or whatever, I would like to see this sort of understanding where you are eliminating that because it's non-permissible value. So for you to even write NPV and to cross it out, that would be, I guess, required in order for you to demonstrate that understanding. So we've gone through the example there, the two different questions, and so I will provide again some assignment questions, some textbook questions that you can work on in order to practice this, and then please let me know what questions you have on that. You notice that there are still two examples within those notes. I will provide a recording on those two examples separately, and so I'll label this one, the one we just did, 3.4a, and I'll label the one to come as 3.4b with the word problems.